Hello, everybody. We are going to continue with video lectures, and I'm going to start from where we left off last time. But first, let me say that I hope all of you are safe and sound, healthy, and please continue to stay home and follow health officials' instructions to continue to stay safe and sound. Okay, so in this first lecture, I'm going to talk about higher order linear ordinary differential equations. Okay, so we are going to consider just one equation, a linear equation, and it's going to be higher order. A higher meaning the order is larger than 1. So since we have just one equation, we have one function y, function of t, and its derivatives. So if you take, I'm sorry, 1 moment. So if you take the derivative of your function, let's say the antiderivative with respect to t, in a more simple notation, we may denote this derivative like this, the antiderivative of y. Now, a differential equation of the form we start with the antiderivative, the highest order derivative of y, and we are going to write our equation where the coefficient of this highest derivative is 1, and then plus some function, say a1 of t, times n minus first derivative of y, plus another function a2 of t times n minus second derivative of y, and we keep going this way until we reach the function y itself, and we set it equal to another function of t. So where these are functions of t, a1 of t, a2 up to an of t, and b of t are functions of t. So such an equation is called nth order linear ordinary differential equation. So nth order because the highest derivative in your equation is order n. Linear because all the derivatives of the function y and the function y itself appear in the first order. Ordinary differential equation because we have only one independent variable t and everything else is a function of that variable. As usual, as before, if this function on the other side of our equation, if that function happens to be 0, then the equation is called homogeneous. All right, now in order to develop methods of solving such equations, we are going to convert this ordinary differential equation into a system. Remember, we worked with systems before. So we want to use the methods we developed in solving systems in solving ordinary differential equations, just one equation. So we are going to convert this equation into a system of first order linear ordinary differential equations. So in one equation, in the equation we want to consider, we have higher derivatives of the function y, and we are going to convert it into a system where the order of each equation is 1, first order system. Now, to do this, we need for an equation, ordinary differential equation, there is one function, y of t. For a system, we need n functions. This n here is the order of our differential equation, highest order of y, which appears in our equation. We need n functions. Remember, we denoted them by x1 of t, x2 of t, up to xn of t. So given nth order, so maybe let me call this, give this equation a name. Let me call it star. Given nth order linear ordinary differential equation star for the function y, we let, so we need to define these functions x1, x2 up to xn. The first one, x1, we let it to be our unknown function y. So this is what we are trying to find. But we need others. So the other functions we are going to call derivatives of y. So x2 is the first derivative of y, dy dt. But since we already called y to be the variable x1, this means the variable x2 is the derivative of the first function x1. And then the variable x3 is going to be the second derivative of y, which is the derivative of the first derivative, but the first derivative is x2, so x3 is derivative of x2. So we keep going this way until we have xn, which is the nth derivative of y, and this is going to be xn minus 1 prime, the derivative of the previous variable xn minus 1. So in this way, we get our n functions. We start with taking the function y, this is x1, and then taking its derivative, we find our second function x2, take the derivative, find our function x3, and continue taking derivatives, take the derivative of xn minus 1 to get our last variable xn. So now what is going to be the equations in our system. Okay, let me see how I can pass to the next page. Okay, hopefully. Okay, here we go. All right, I'm going to also share the PDF file of these notes, so maybe you or you can stop the video anytime and go back to, if you don't remember what was written before, you can always stop the video and go back to the previous screen. But also the whole notes I'm going to share also as a PDF files, so you don't need to copy the notes. Just try to follow how I'm working it out. But okay, just to remember, so we have our first variable x1, which is y, and then x2, which is the derivative of y, so x1 prime. And we keep going like this. So xn minus 1 is the n minus first derivative of y. So this is xn minus 2 derivative. And the last one, xn, nth derivative of y. So this is xn minus 1 derivative. So these are the functions. So these are the functions. Now, what about the equations? Differential equations, of course. So remember, in a system, we have equations of the form x1 prime equal to x2 prime equal to, and so on, xn prime equal to. We have first order equations, so we take derivatives of our functions. So what are the equations? But the equations, we go back to the definition. In the definition of the functions, x1 prime, okay, for x1 prime, go here. So x1 prime is equal to x2. For x2 prime go to the next equation. x2 prime is x3. Okay, so xn minus 1 prime is xn. Sorry, xn minus xn. That's right. I'm sorry. So x1 prime is x2, x2 prime is x3, xn minus 1 prime is xn. Now, what about xn prime? What is the derivative of xn? But that comes from our equation star. Remember, this comes from, we are trying to solve the equation star. We have nth derivative of y plus a1 times n minus first derivative plus up to an, the function y, equal to the function b. So remember, xn is y to xn is the nth derivative of y. No, I made a mistake. I'm sorry. Let me go back up, and numbering is wrong. I'm sorry. Yeah, okay. You see here, x2 is y prime. x3 is y double prime. So xn should be y to the n minus 1. Okay? So we go up to n minus 1 because we start with x1, and x1 is the 0th derivative, if you want, just the function y itself. So x2 is the first derivative, x3 is the second derivative, and the last one, xn, is the n minus first derivative of y. Okay, I'm sorry about that, but it's still true that it is xn minus 1, derivative of xn minus 1. All right, so let's go down and I'm sorry, it's giving me some trouble here, my cursor. So where's my cursor? Okay. Okay. All right. So let me correct this. n minus first derivative. Okay. N minus first derivative. So derivative of xn is going to be the nth derivative of y. And from equation star, the nth derivative of y is equal to, let's take all these terms with a's to the other side, minus a1 times n minus first derivative, minus, we go up to minus an times y plus the function b. But n minus first derivative of y is the function xn. N minus second derivative of y is the function xn minus 1. And the function y is the function x1 plus b. So our last equation, the derivative of xn prime, which is the nth derivative of y, is, let me start writing from the term x1, minus an times x1, minus an minus 1 times x2, minus up to minus a1 times xn plus b. So from just one equation star, we get this system of n equations, but n system of n equations, but all of them are first order. So maybe summarize. We have this equation, the nth derivative of y, plus a1 times n minus first derivative of y, plus up to an times the function y equal to b. Then we let x1 equals y, x2 equals y prime, and so on. Xn equals n minus first derivative of y, and we get the system x1 prime equal to x1 prime equal to x2, x2 prime equal to x3, n minus 1 prime equal to xn, and xn prime equal to minus an x1 minus up to minus a1 xn plus b. Okay, so this is how we convert nth order ordinary differential equation into a system. Okay, so maybe at this point we can consider an example to understand this better. Okay, let me see. I didn't go. Okay, so let's work out an example. Convert the equation what is our equation? We have third derivative of y plus 3 times second derivative of y minus t times first derivative of y plus 2 times y equal to cosine t. So this is our equation. Convert the equation into a system. So this is a third order equation, n equals 3. So we are going to have 3 variables. We have x1, which is y, and then x2, which is derivative of y, and x3, which is the second derivative of y. So if I take x1 prime, that's derivative of y, which is x2. If I take x2 prime, that's derivative of y prime, which is y double prime, which is x3. And if I take derivative of x3, this is the third derivative of y. And from the equation, the third derivative of y is equal to minus 2y, but y is x1, plus t times y prime, but y prime is x2, minus 3y double prime, but y double prime is x3, and then plus we have cosine t. So this is the system. The equation is converted into the system, and the relation between the two, the important relation, is that the unknown function in the equation, the unknown function y in the equation, is the first variable x1 in our system. Okay. Now, we are going to remember how we worked in for systems. We write it in the matrix form. So in matrix form, our unknown x is a vector now. It has three components, x1, x2, x3. The matrix A is the matrix of coefficients in the system. So in the first equation, we have only x2, so no x1. x2 is coefficient of x2 is 1, coefficient of x3 is 0. In the second equation, there is no x1, no x2, coefficient of x3 is 1. And in the last equation, coefficient of x1 is minus 2, coefficient of x2 is t, and coefficient of x3 is minus 3. And we have the function b, the vector function, on the other side. In the first equation, there is no constant function, not the constant function, but function of t only. So in the second equation, no function. In the third equation, we have the function cosine t. So we can write the system as dx dt, derivative of this vector function, is matrix A times the function x itself plus the term b. Okay, so let's write this matrix form for nth order ODE. The system is, so let's remember the system, x1 prime equals x2, x2 prime equals x3, up to xn minus 1 prime equals xn, and xn prime equals minus an x1 minus an minus 1 x2 minus up to a1 xn plus b. So our unknown function, vector function x, has n components, x1, x2, up to xn. Our matrix A, since we have n equations in n functions, is going to be an n by n matrix. In the first row, we have 0, 1, and then zeros. In the second row, 0, 0, 1, and then zeros. The one before the last row, 1 at the end. And for the last equation, the coefficients are minus an minus an minus 1, and the last one is a1. This is an n by n matrix. and the function on the other side of our equation, 0 until the last one, and the last one is b. So the system, again, in matrix form, derivative of x is matrix A times x plus b. Okay, so we convert the ordinary differential equation, nth order equation, we convert it into a system like this. All right. Now, from theory, from the theory of systems, we know that this system has n independent solutions. Since we have an n by n system, it's going to have n independent solutions, say x1. I mean the solutions of the system. I'm talking about the system, so the solutions are vectors. Remember, in our system, the unknown is vector function x, so all solutions are vector functions. We have n independent solutions, and the general solution is a general solution. We write as C1 times x1 plus C2 times x2 up to Cn times xn. Okay, so now we started with nth order ordinary differential equation. We converted into a system, first order system, n by n system. This system has n independent solutions. Now, how do we read solutions of our equation from these vector solutions? Remember, our unknown function y is the first component of our vector function x1. So first components of the solutions, vector solutions x1, x2 up to xn gives, since we have n solutions, we are going to have n first components. So they give n independent, again, since these vectors are independent, because of the nature of the matrix A, in our system, it's a special matrix, not any matrix. It's the matrix coming from one equation. So all the first components of the solutions are going to be independent. So gives n independent solutions, y1, y2, yn. Okay. So once we find vector solutions of the system, to find solutions of our ordinary differential equation, we just take the first components. The first components of each solution. They are going to be just one function. I'm just talking about the components. So the first component is just one function. But since we have n different first components, we are going to have n different independent solutions of our equation star. Okay. All right. So we know that they're independent, but how do we know that there is nothing else? Because okay, let me see. Oh, oops! I don't want to go up. I want to go down. All right. Okay. So how do we know that there is nothing else? Now, star and the system are in correspondence. So every solution correspondence. So every solution of the equation star gives us a solution of the system, and solution of the system gives us a solution of the equation star. So y1, yn are the only independent. No, that's not true. You may have some other solutions, of course. Um, uh, are the maximum number. How should I say this? So y1 through yn gives the general solution of the equation star. So the general solution is c1 times y1 plus up to cn times yn. In other words, the set of functions y1, yn is a basis for the solution space of the equation star. So remember, star is nth order. And the basis has n elements. From linear algebra, any other basis is going to have, again, n elements. So any n independent solutions, y1 up to yn, gives a basis for the solution space. Okay, so of course, we are going to get these functions from solutions of the system, but here I'm talking in general when you have, so for nth order equation, n independent solutions gives a basis. Now, so let's say somehow, without referring to the system or anything else, because in general solving systems is it may be hard. Let's say somehow you're given n functions, which you know to be solutions of your equation. How do you know that they are independent? To check for independence, we check the Wronskian. So Wronskian of n functions, y1 up to yn, it's going to be an n by n determinant. So in the first row, you write the functions. In the second row, you write the derivatives. And second derivatives, third derivatives, up to n minus first derivatives. N minus first. Okay, this is n by n determinant. So since in the first row you write the functions themselves and then the first derivative, second derivative, you stop at the n minus first derivative to get an n by n determinant. If the Wronskian is not identically zero, meaning in general, this Wronskian is going to be a function of t again, because the solutions y1, y2, yn are functions of t. So Wronskian is going to be a function of t. Not identically zero means there is a point t0 where Wronskian is not zero for some t0. If this is the case, then the functions are independent. y1, yn are independent. Let me show you an example where we use this Wronskian to see, to check for the independence. Okay, so given the equation, oops, I'm sorry. Okay. Given equation, t cubed times the third derivative of y plus t squared times the second derivative of y minus 2t times derivative of y plus 2y equal to 0. Check that the functions y1 given as t, these are given in the problem, the functions. You are not supposed to come up with these solutions yourself. These are given in the problem, part of the question. So the function y1 is t, y2 is t squared, and y3 is 1 over t are solutions for t greater than 0. Now we have the function 1 over t. Remember, for solutions of differential equations, we consider them always on an interval. So saying that t is different from 0 is not enough. We need to give an interval. So the given interval in the problem, this is also given in the problem, the interval is t greater than 0. Find all solutions. Okay, so checking that we have the equation and we have the functions. So to check the functions, so first check the first one, y1 equals t. we just take derivatives and plug into the equation, see that if the equation is satisfied. So y1 prime then is 1, y1 double prime is 0, and y1 triple prime is also 0. So in the equation, t cubed times y1 triple prime plus t squared times y1 double prime minus 2t times y1 prime plus 2 times y1. So y1 triple prime is 0, y1 double prime is 0, y1 prime is 1, and y1 is t. So we have minus 2t plus 2t. This is 0. So it is a solution. So for y2, which is t squared, y2 prime is 2t, y2 double prime is 2, y2 triple prime is 0. So if you check the equation, t cubed y2 triple prime plus t squared y2 double prime minus 2t y2 prime plus 2y2. So y2 triple prime is 0, y2 double prime is 2, y2 prime is 2t, and y2 is t squared. So we have 2t squared minus 4t squared plus 2t squared, which is again 0. So this also checks. And finally, for y3, 1 over t. So y3 prime, derivative of 1 over t minus 1 over t squared. y3 double prime, 2 over t cubed. Be careful about the minus signs. And the triple prime is minus 6 over t to the 4. So equation t cubed y3 triple prime plus t squared y3 double prime minus 2t y3 prime plus 2y3. So y3 triple prime minus 6 over t to the 4. Y3 double prime, 2 over t cubed. Y3 prime minus 1 over t squared. And y3 is 1 over t. So we have minus 6 over t plus 2 over t plus 2 over t plus 2 over t, and that's again 0. So this also checks. So y1, y2, y3 are solutions. The equation is third order. So we expect 3 independent solutions. But so y1, y2, y3 are 3 solutions, but the question is, are they independent? Are y1, y2, y3 independent? And we check this using the Wronskian. So what is the Wronskian of the functions y1, y2, y3? So this is the 3 by 3 determinant. In the first row, we write the functions. In the second row, we write the derivatives. And in the third row, we write the second derivatives, 2 over t cubed. So I'm going to expand this determinant using the first column because we have a 0 in the first column. We have t times the 2 by 2 determinant, 2t minus 1 over t squared, 2 2 over t cubed. And then next one comes with a minus sign. So minus 1 times the determinant, t squared, 1 over t, 2 over t cubed. Plus 0. We don't need to write it down. Okay, so t times, when we multiply the main diagonal, we have 4 over t squared minus the other diagonal is minus, so it makes it plus 2 over t squared. So minus the main diagonal, 2 over t minus 2 over t. So that's 0. Here, 4 plus 2 is 6. So the whole thing is just 6 over t. And remember, t is positive. We are in the interval, t greater than 0. So the Wronskian is never 0 in this interval. So this means y1, y2, y3 are independent. So this means any solution, or we can say general solution, y has the form so a general solution is of the form c1 y1 plus c2 y2 plus c3 y3. So it is of the form c1 times t plus c2 times t squared plus c3 times 1 over t, so c3 over t. But remember, this is on the interval t greater than 0. And c1, c2, c3, any constants, but real constants, remember. So this gives us, we have a third order equation. We have 3 independent solutions. So they form a basis for the solution space, meaning the general solution can be written as a linear combination of those 3 functions. And for constant c1, c2, c3, this gives us all solutions of the equation. Okay, so I want to stop at this point. We are going to consider now to obtain those solutions, but in general, it's going to be a hard problem. So next, we are going to consider, first of all, so linear. First, we are going to consider homogeneous equations. And in order to obtain solutions, we need coefficient functions to be constant coefficients. And we will see how to obtain solutions of such equations in the next video. So that's all for this video. See you later, or talk to you later.